All right, folks, we're going to kind of switch gears here a little bit. The next section we look at is called Numerical Integration. So we're going to take a brief look in this section at numerical integration. Recall back when in Calculus 1, when integration was first introduced, and specifically when we were talking about the area under a curve problem, rectangles were used to give an approximation. If you were in my Calculus 1 class, at that time we discussed a left sum approximation and a right sum approximation. Both of those approximations were the result of using rectangles. And we also wrote two programs for your calculator, the left sum program and the right sum program. Both of those programs were examples of numerical integration. Now your graphing calculator, it also has a built-in numerical integration feature. But at this time, we're going to add one more numerical technique called the Trapezoidal Rule. Now, as the name suggests, we're going to use trapezoids to approximate the area rather than rectangles. Now, folks, at the Blackboard site, you will find a handout in the course content area for this material. Hopefully you have that handy. I'm going to hit some highlights from this handout now. And at the very end of the handout, there's a calculator program for the trapezoidal rule that I will go over that as well. So let me call that up right now. Here's the handout. So this is the handout, the PDF that's at the Blackboard site. Like I said, you can read it on your own. I'm just going to go through it, very quickly. This example 1 that I have here is kind of a review of what we did initially back in Calc 1. Given a function, you can approximate the area using rectangles. So there's the graph of the function, and there's, you see 4 rectangles. It looks like they're left sums. A was the left endpoint of the interval, B is the right endpoint. This is all old stuff. That's how you find the area of each rectangle, and you added the area of the rectangles to get an approximation. So here's the function again, and now we're going to use trapezoids to approximate the area. So in here, I've sketched 4 trapezoids. So here's trapezoid 1. Here's trapezoid 2, trapezoid 3, trapezoid 4. So there's only 4 trapezoids in there. And I think just by eyeballing it, it looks like 4 trapezoids will give a better approximation than what 4 rectangles did. So now, the one thing we need to remember from geometry is the formula to find area of a trapezoid. Now, you may remember the formula as being 1/2 the quantity b sub 1 plus b sub 2 times h, where b sub 1 and b sub 2 were called the bases of the trapezoid and h was called the height. What was hopefully stressed to you back in geometry is it doesn't matter if you call those two sides bases or heights. The important feature is the two sides that are parallel in a trapezoid. Because, let's look at trapezoid 1 here. Here's trapezoid 1. Because of its structure, the two sides that are parallel in trapezoid 1, they remind me of heights. So the formula for area of a trapezoid will be 1/2 the quantity h sub 1 plus h sub 2. That's the sum of the two heights times b. Here's b, the base of a trapezoid. So another way to remember it, and this is kind of how I always remembered it, the formula for area of a trapezoid is I take the average of the two parallel sides and then multiply it by the other side. So h sub 1 plus h sub 2, as I said, those are the two parallel sides. 1/2 times this quantity is getting the average. And let's see. Now, this first example is we're looking at that same function, and now we're going to use 4 trapezoids to approximate the area. So we're going to actually go through the process of finding the area of each one of these trapezoids, add it all together, and use that as our approximation. And you could read through on your own to see how we find by hand the area of each trapezoid. And then we add them all up and we get 43 over 3 as the sum of those 4 trapezoids. Now, if we actually do the calculus, we get an antiderivative and we use the fundamental theorem of calculus, we're going to see that the exact area is 40 over 3. 4 trapezoids, which gave us 43 over 3, it's not too bad of an approximation. So, here, this is just generalizing the work that we did. That in general, those heights are found by evaluating the function at values of x. Delta x is, the base of a trapezoid. So, for example, if I look at, if I just come in here and look at trapezoid 2. So, trapezoid 2, its area is 1/2. Quantity. This height is f of x sub 1. This height is f of x sub 2. And then the base is delta x. So, and we see that right here. So that's how you find, in general, the area of any, 4 trapezoids. And then, we add them all up. And then I'm doing just a little bit of algebra. So I'm taking all of this mess here and I can factor out, because each term in here has a common factor of 1/2 delta x. So I'm factoring out a 1/2 delta x, or a delta x over 2. And that leaves me with this mess. And just a little bit of algebra. You see you have 2 of the f of x sub 1s. You have 2 of the f of x sub 2s. And you have 2 of the f of x sub 3s. So this is kind of what it generalizes to. And it's this last equation here that kind of generalizes what is known as the trapezoidal rule. And then I have, in general, if you use n trapezoids, then the approximate value of the definite integral is given by the trapezoidal rule. And, here is the trapezoidal rule. So, again, you can, read through all that on your own. I have some notes here. To get a better approximation, we'll use more trapezoids. There is error involved in the trapezoidal approximation. The formula to compute the error, let's just say it's just worth noting that when we double the number of trapezoids, that reduces the maximum error by a factor of 4. It's a very, very pretty good approximation. All right, you can read through example 3 on your own. It's using the trapezoidal rule, going through it by hand, but the structure of the trapezoidal rule is ideally suited for us to write a program. And here we are getting to the program. So now the program, it starts here and it continues on to the next page. But let me back up here. So what I'm going to do is I'm going to call up my calculator and I'm going to go through and I'm going to actually enter the program on my calculator. So these are the lines of code over here. So in case you forget how to write a program on your calculator, you'll click program. And let's see, I'm creating a new program. And the name, well, I need to give it a name, so I'm just going to call it Trap. That's a nice name. So the first line, DISP, that's a program command. So DISP, that's short for display. I think there it is. It's an IO, so it's a number 3. The quotes, let's see, the quotes are right here above the plus sign in green, so I better hit the alpha button first. quotes, and now I'm going to type out enter function in. I'm going to lock my keyboard into alpha mode so I can do this quickly. So enter, that's E-N-T-E-R space. This will give me a space. Function. So just, getting this written in. And if you need to pause, feel free to, so you can, follow along. In, and then another space, y sub 1. Okay, y sub 1, that's hidden under vars. So I go over y vars function. So there's y sub 1, and now I need quotes. So quotes. Okay, I go to a new line. Prompt A, comma B, comma N. So prompt, that's a program command. So program, I believe it's an IO. Yep, number 2. A, so alpha A, comma, comma's right here. B, comma, N. All right, so new line. Y sub 1 evaluated at A plus Y sub 1 evaluated at B. Oh, I'm sorry. New line, B minus A, that quantity divided by N gets stored to D. So parenthesis, B minus A divided by N, and that gets sent to D, or it gets stored in D. Oops. Oh, nope, I lost it. Oops, sorry. Let me come back. Edit, come down. So I'm storing that in D. So alpha D. So real quick, here's it tells you over here to the right. It tells you what each line of code is doing. So I don't have to tell you because it's being told. Next, y sub 1 evaluated at A plus y sub 1 evaluated at B. That gets stored in S. So y sub 1, remember that's under vars, y vars, y sub 1 evaluated at A plus y sub 1 evaluated at B. That gets stored in S, so alpha S. Enter for a new line. A plus D, that gets stored in X. So A plus D, that gets stored in X. New line, LBL1. LBL is another program command. So, oh, here it is. It's a CTL, it's a control. So that's number 9. So LBL1. New line, 2 times y sub 1 evaluated at X. So y sub 1 evaluated at X plus S. That gets sent back to S. So it's updating it. Okay, new line. X plus D, that gets sent to X. So X plus D, that gets sent to X. Okay, if that'll be a program. Oh, there it is, number 1. If X is less than B. Okay, less than. I believe less than is hidden under test. So second math. Yep, there it is, number 5. So if X is less than B, new line, and oops, I just wanted to scroll down a little bit. So my next line is then. Then that's hidden. That's a program command. It's number, once I hit the program button, I see it's number 2. New line, go to 1. So go to, that's another program command. LBL matches up with go to, so it's right there. So go to 1. And then the next line is S times the quantity D over 2. So D divided by 2. That gets sent to S. New line, display. So that's a program command. 3, and then quotes. Quotes. Oh, you know what? I'm gonna lock my keyboard into alpha mode. Let's see. Trap. Approx. So trap, and then I need a space. Approx. So that's APPROX, and another space is quotes. Okay, I need to get out of alpha mode. Comma. Here's the comma. And S. So alpha S. All right, so I should have the program entered. And, let me just quit. And I'm gonna go back to the slides. So again, if you need to pause, rewind, because I just went through that, kind of quickly, but get the program entered into your calculator, because now that I've entered the program into the calculator, I want to run it to ensure that it's good to go. And so hopefully I don't have to do any troubleshooting. So I'm going to run the trapezoid program we just entered for n equals 10 and n equals 100. In other words, 10 and 100 trapezoids, to approximate the integral from -1 to 1 e to the -x squared dx. So let me get my calculator back up here. So the first thing is, I have to put the integrand, I have to put that into y sub 1. So e to the -x squared. All right, so now I can quit. Now I'm going to run the program. So the program was, I called it trap. So I hit enter, and it reminds me to enter the function in y1. Okay, I did that. A, that's my lower limit of integration. So -1. Enter. B, that's my upper limit of integration. 1. Enter. N is the number of trapezoids. And what did I say here? I said 10 and 100. So we'll do 10 first. Enter. And it didn't show me anything. Oh, it didn't show me anything. So that means what I have to do is I have to go back to my program. I have to go back to my program. I have to edit. I have to see where I screwed up. All right, so it looks to me like everything is fine here, except I left out a line. After go to 1, I left out the line else. So this is what happens sometimes. When you get to be old like me, you skip a line. So I need to insert. So I'm going to insert a new line, and I need to get the program in here. program command, else. All right, I'm sure some of you noticed that I skipped that line as I was doing it. I didn't. But when it didn't work, that told me I had to debug the program. I had to problem solve. I had to go back and look and see where I screwed up. So let's quit. Again, I'm going to check. I do still have y1. I still have the function in y1. So let me try to run the program this time. 4. A is -1. B is 1. Number of trapezoids, 10. And it tells me the trapezoid approximation is 1.488736668. Now I'm supposed to do it with 100 trapezoids. So let me try it with 100 trapezoids. -1. B is 1. 100 trapezoids. 1.493599214. And if you're wondering, well, how do we know if these numbers are actually correct? Well, on the handout, you will see on the last page, table 7.5.1, it has the trapezoidal approximation for this definite integral for n equals 10, 50, and 100 trapezoids. And I see I'm getting the numbers that's shown in this table. So my program is working just fine. And you know, earlier in this screencast, I mentioned your calculator had built-in numerical integration. So let me show you that while we're here, just in case you're not familiar with it. Your calculator's, let me clear that. Your calculator's built-in numerical integration is hidden under math. And see, you know, for me, number 9 is, you know, well, it's where it's hidden. It's, this is the numerical integration. So I hit enter and, you know, it looks like this. So I have to tell it what function to integrate. Well, I'm going to do this function. It's the function that I already have in y sub 1. So I go over y sub 1, comma, the variable of integration is x, comma, lower limit of integration is -1, comma, upper limit of integration is 1. And so that's the calculator's built-in, you know, numerical integration. And if, you know, if you bear with me, some of you may see when you use the calculator's built-in numerical integration, you may see this. I mean, that's pure WYSIWYG. What you see is what you get. So, you know, lower limit, -1. And then I'd go up, the upper limit is 1. My integrand, well, keep in mind I have that function stored in y1. So I'll go over and just call up y1. And then my variable of integration is x. So that's it. Although I do have one more comment about this section. You know, feel free to read the section. You know, in the reading, you're going to see one more numerical technique mentioned in the reading. It's called Simpson's method. Simpson's method is predicated on using parabolic segments to come up with an approximation. But, you know, that's it. That's it for this section. You know, I don't have much homework for you to do in this section, but the homework that I do have for you, you know, just do the problems by running the program, doing the trapezoid program, and just run it for, say, you know, 100 trapezoids. And then you could check it by looking at the calculator's built-in numerical integration. But that's it for this section, kind of short and sweet. Thanks for watching.